All right, so we know that the driving force behind plate tectonics now is convection currents. And if we apply those convection currents in the mantle, which is a fluid-like material, we'll see how they can start to drive the plates, which sit above it right here, moving the plates all around. Well, what we want to look at is what happens now at these boundaries because of these convection currents. This figure shows three different types of boundaries between two plates that move relative to each other. We have plates that are moving away from each other, they're spreading, plates moving towards each other, they're colliding, and plates that are moving parallel but in opposite directions. The three types of boundaries can also be observed between these lithospheric plates we've been studying, and we'll take a look at that now on the following pages. All right, first up, when two plates are moving towards each other, we say that they are converging. There are three types of converging plate boundaries where two plates crash into each other. There's oceanic versus oceanic plates, oceanic versus continental plates, and finally continental versus continental plates. The map on the left shows that Japan is situated close to the boundaries between three lithospheric plates. The figure on the right shows a cross-section through the crust in the region. The Pacific plate is subducted or moves below the Eurasian plate. In this area, both the plates are actually oceanic plates, so this is an oceanic plate boundaries. Much of the melt that comes from the Pacific plate subducting or moving underneath, much of the rock will melt into magma and will push its way up to the surface and rise up and become volcanoes at the surface. By this mechanism, volcanic islands are continuously being built up around these subduction zones where one plate gets forced down under another plate. In geology, such islands are referred to as island arcs because there's a curve or an arc to the island that mimics the plate boundary. Thus, Japan is actually an island arc. Now, the map to the left here shows the occurrences of earthquakes that were registered near Japan in a 20-year period from 1975 to 1995. Each point indicates an earthquake, and the color indicates the depth of the earthquake focus, which is the origin point. Notice the orange would be the shallowest, then to yellow, green, blue, pink, and the deepest ones would be to the red. Note that the shallowest earthquakes occur in the east, all along the edge over here on the right-hand side, all the orange and yellow points, while the earthquakes become deeper and deeper as we start to head to the west. In a section from east to west, the depth of the earthquake foci, which is plural for focus, reflects the depth of the subducted slab. So what you'll see here is right over here we have shallow earthquakes. That's going to be right here where they rub against each other, but very shallow, not too deep underwater. As we start to travel west, notice how the boundary gets deeper and deeper and deeper. Now the earthquakes are going to occur very, very deep underground as we travel further to the west. And you'll see that as we travel further to the west, the earthquakes in fact did occur deeper underground. All right, next along the west coast of South America, the oceanic Nazca plate is subducted below the continental South American plate. So here, instead of oceanic, we have an oceanic plate versus a continental plate. This type of geological setting is the same way as the region around Japan, except that it's continental versus oceanic. And what we're going to have happen again is subduction occurring and some extra magma created from the melted rock, which makes volcanoes, except here we have a landmass, a continent, where these volcanoes are. And again, if we take a look and map the earthquakes, I bet the earthquakes will get deeper and deeper and deeper as we travel inland into South America. And here's our map that shows that. So as we take a look, the plate boundary is right about here, just off the west coast of South America, right here. And as we travel further to the east, the earthquake centers get deeper and deeper, because the plate dives deeper and deeper and deeper down below. All right, next up is a continental versus continental plate boundary that you see right there. Well, the first thing that's happening here, if we take a look at it, is the oceanic plate in the middle is much denser. So the entire oceanic plate will subduct under and underneath the continental plates because its density is 3.0 compared to theirs at 2.7. So it's much, much denser. Okay. However, with the continental plates having a much lower density, the continental crust cannot be subducted, and this animation shows the destruction of the oceanic crust underneath. But when the two converging continents meet, the subduction stops and the continents simply collide into each other and actually push upward, forming a mountain. Well, we'll see this here with India. About 225 million years ago, India was a large island situated off the coast of Australia. If you remember, back in Pangaea, it was separate from Asia and actually connected down by southern Africa, Australia, and Antarctica. Well, what happened was, as India broke apart, it moved northwards, and at about 40 to 50 million years ago, India collided with the European continent, as you see here. The northernmost part of the Indian subcontinent was forced below the Eurasian continent, which resulted in a thickening of the crust. And the mountain chain, the Himalayas, were formed, which has Mount Everest, which is the tallest mountain in the world. So this is how we got the tallest mountain of the world. The collision between the two continents continued, and over time, it's continuing to happen over and over and over again. In fact, Mount Everest is actually growing a couple of centimeters every year. So the Indian continent, it's actually still moving northward, and the Himalayas continue to rise about 1 centimeter every year. Well, if we take a look at this, when we look at the earthquakes again, the map to the left shows the occurrences of earthquakes that were registered again in that 20-year period, and relative to the movement. So we're going to see the India subcontinent is right here. Here would be the point of India, and the earthquakes are right where the top of India meets the rest of Asia. And right here, with all of these earthquakes occurring, where the two crash into each other and the mountains rise up. But notice they're mostly red in color, which shows that they're shallow earthquakes. Why? Well, because there's not much subduction happening, because as they crash into each other, they're going to push upward, that we see happening here, and just like we see happening here. As India crashes into Asia, it's going to push up. So there is our continental plate collision. All right, next up are what are called diverging plate boundaries. Diverging means to move apart. So when two lithospheric plates are moving away from each other, it can be said that they are diverging. Think of it like dividing, moving apart. This picture shows two oceanic plates that diverge along the mid-ocean ridge, much like our mid-Atlantic ridge we studied before. Below the mid-ocean ridge, the asthenosphere occurs at a higher level than normal. See how it kind of pushes up here? Because of this, the material in the asthenosphere undergoes partial melting, resulting in the formation of basaltic magma here. So we get this magma chamber. After the formation, the magma moves upwards to a chamber that's positioned just below the surface. When the two plates move away from each other, the empty space between them here is filled with this magma. It's immediately filled with the magma that comes up from the magma chamber. The magma immediately crystallizes in a couple of seconds and forms new oceanic crust. And if you remembered with seafloor spreading, this will then rip apart again, pull this section to the right and this section to the left, creating a brand new opening which will fill with more magma, even younger magma. And that's how we had our different ages, with the youngest rock being right along the mid-ocean ridge. And we'll see that happening here. So as the plates move apart, the magma fills in and we get younger rock right in the middle. Now, if we apply this separation happening, it's right here along our mid-ocean ridge where it's separating apart, looking at the map from earlier on. If we take a look at this, we get an interesting thing happening right here. There's one section on the Earth where a portion of the mid-ocean ridge is actually no longer underwater, and that's Iceland right here. And Iceland is actually very volcanic. So if we go and we take a look at these diverging plates, we'll see right here where Iceland is right on the plate boundary. So the North American plate is slowly moving west relative to the Eurasian plate, which is moving to the east. The boundary between these two plates is called the Mid-Atlantic Ridge. Well, new ocean crust is more or less continually generated right along this mid-ocean ridge. The mid-ocean ridge can flow across Iceland like we see happening here. So the western part of Iceland belongs to the Eurasian plate, where the western part belongs to the North American plate. Because the two plates are moving away from each other, the width of Iceland increases about 2 centimeters every year. 1 centimeter moves to the right, and 1 centimeter moves to the left. So the plates do move However, they move about 1 centimeter a year, which is about as fast as your fingernails or your hair grows. So you can't see it, but they do happen. They can be measured over a year's time. All right, if you take a look here, the map to the left shows the occurrences of earthquakes that were registered in that same 20-year period along the mid-ocean ridge, and only shallow earthquakes occurred. There are no deep earthquakes. Why? Because the two plates simply separated from each other, like we see in this picture here. There's no subduction happening at all. They're just simply moving away from each other. Okay, now let's take a look at diverging plates between two continents. And the only place you're going to see this happen is in Eastern Africa. It's called the East African Rift, and it's kind of right here, and that's what makes these really high waterfalls here. Some of the tallest waterfalls in the world are here, as the portion of Africa is literally being ripped apart. So the boundary between the African plate and the Somalian plate is called the East African Rift. The two lithospheric plates are moving away from each other. Now, when two continental plates are moving away from each other, we get what's called a continental rift formed. And below continental rifts, magma is generated by partial melting of the mantle. Thus, rifts are associated with a lot of volcanism. We have a lot of volcanic activity happening here. If the African plate and the Somalian plate in the future continue to move apart from each other, an ocean will form between the two continents as they're separated. Much like when Pangaea separated, we had an ocean form in between them called the Tethys Sea. And later on, as time moved on and Africa and South America separated, that started to form an ocean, which we now call the Atlantic Ocean. So if we take a look here with our earthquakes again, we will see a definite pattern of earthquakes almost forming a line or a zipper right through here, and this is where the separation is occurring. And notice they're shallow earthquakes again, which show a separating movement, no subduction or sinking happening. All right, our third type of movement is what's called a transform fault, or strike slip faults that extend through the rock. Here, they're moving side by side in opposite directions. Well, California is known for this, the famous San Andreas Fault. It's the best known fault in the world. It's actually the star part of the original Superman movie. If you ever saw that movie, or if you rent it, take a look at it. And the whole evil plot is to land a nuclear warhead right on this San Andreas Fault to make this portion of California fall into the ocean, because the villain Lex Luthor purchased all this cheap desert land right here that would then become oceanfront property. So if you take a look at that movie, you'll see some good plate tectonics in it. All right, so here we have the San Andreas Fault. It's the boundary between the Pacific Plate and the North American Plate. So a pretty cool thing, Los Angeles and San Francisco and Baja California here, it's actually part of the Pacific Plate. So Los Angeles is not on the North American Plate, yet San Francisco is. And check it out, over time, as it moves about 5 to 6 centimeters per year, and that's what causes all the earthquakes, Los Angeles will eventually move its way up and be neighbors with San Francisco. So here we see a transform fault as the section to the left moves towards the north, and the section towards the right kind of stays and moves due west, so we get a side-by-side motion happening here. If we take a look at the earthquakes here during that same 20-year period, we see only shallow earthquakes occurring here. Again, no subduction happens, and that's shown by our shallow earthquakes. All right, next up would be what's called hotspot volcanisms. Now, what a hotspot is a section in the Earth's crust where magma is able to push its way through. The most famous place you'll see this are the Hawaiian Islands. Each of those Hawaiian Islands is actually a hotspot where magma pushed its way through the ocean floor, cooled, formed solid rock, but over time it grew big enough to actually make islands that popped above sea level. So you can see it's almost like an island-making machine. What we know is that the islands are moving towards the northwest, and the northwesternmost island, Kauai, is the oldest island, and they get younger and younger and younger as you move down towards the southeast, with the big island of Hawaii being the youngest one of all, only 500,000 years old at the oldest. In fact, it's still volcanic now. Right here is where Kilauea is, which is the active volcano on Hawaii. So you can see that everything is moving in this direction. There used to be a volcano here called Mauna Loa, and it's no longer active, but Mauna Kea is, and portion of this second mountain on the Big Island is Kilauea, which is the actual active volcano that's there today. Well, Hawaii moves pretty fast, about 11 to 12 centimeters per year. So this is, we see a little bit more. Okay, so we're looking here and seeing some of the velocities and some of the ages of the rocks. So you can see where the red is, that's the youngest ages. So we see separation happening here in the mid-ocean ridge. So we're kind of tying everything together here. It gets older as we head to the left and equally older as we head to the right, mirror image on each side. If we go here, the Eastern Pacific Ocean, this is what's called the East African Rift, and this is moving to the east, getting older as we head out. This is moving to the west, getting older as we head out. So you can see these are all diverging boundaries here. Over here, we have our old ocean here, the oldest ocean of all, when we look at our timeline, over 25 million years old, and this is actually dying when it dives into the subduction zone here. The deepest part of the ocean is here, called the Marianas Trench. All right, so to summarize everything here, we are going to reconstruct Pangaea. So what we know is that 440 million years ago, Africa and South America were situated near the South Pole. That's how we had those glaciers there. While Norway, circled way up here in red, was situated a little south of the equator, which would put North America and Pennsylvania, places like that. Oh, here's the Great Lakes, up by the tropics as well, which is what gave us our vegetation from the jungles, which turned into coal eventually, and why we have coal mines there. So in this animation, we're going to show how the lithospheric plates moved during the last 440 million years ago. Okay, so as we take a look and move it through, we can see how they have moved over time. We're backing it up. There's the Tethys Ocean. We're bringing North America and Asia back in. So 250 million years ago, we're starting to move away from the South Pole. Now about 200, 150 million years ago, we're going to separate and start to form the Atlantic Ocean happening here. About 100 million years, you can see the Atlantic Ocean. As time goes on, there's India crashing into the Himalayan mountains. Notice how the Atlantic Ocean opened up a lot more with that mid-ocean ridge. So here was the formation of Pangaea and how it's separated to where we are.